Hello everyone, welcome to lesson 4-4, linear functions. As we've done with the other lessons in chapter 4, we will continue to address the question, how can we model relationships between quantities? And we will address the following expressions or vocabulary: linear function, continuous data, and discrete data. For a real-world example, let's take a look at this example here of a jet, or a blackbird, what they call, up, up, and away. The Lockheed SR-71 Blackbird has a top speed of 36.6 miles per minute. If x represents the minutes traveled at this speed, the function rule for the distance traveled is the total number of miles times the speed or the rate times the number of minutes, right? X will represent the number of minutes. So when we multiply the number of minutes traveling at 36.6 per minute, we will get the total distance traveled. Make sense? So our input, which is x, will be 1 minute, 2 minutes, 3 minutes, 4 minutes, and so on. Our rule is that we have to multiply 36.6, so that's our rate per minute, times each minute. This will give us how much traveled in 1 minute. This will give us how much it was traveled in 2 minutes, and so on. The output is y, is our total distance traveled, right? And then we have our ordered pairs, our input and output, our coordinates to make if we wanted to graph this so that we could make a linear function or a linear graph. So let's fill in here what we have. Continuing the pattern of the input, we know that for 3 minutes it's going to look like this. I'm going to pick red. 36.6 times 3 and 36.6 times 4. Okay, now our output, what is that going to give us? Well, I actually have to multiply it. 36.6 times 2 will be 73.2. Okay, so that's the distance traveled, 73.2. Times 3 it is 109.8, and 36.6 times 4 is 146.4. So these are all in units of miles. So that's how much it would travel. 146.4 miles in 4 minutes. That is incredibly fast. And then our order pairs. As we've done here, our input is x and our output is y, or we can say domain and range. We continue with that. So our next domain is 2 minutes, and it's 73.2 on the range, or the y. Okay, 0.2. And for 3 minutes would be, my domain would be 3 and my range would be 109.8. And for 4 minutes, it would be my x value is 4 and my y value is 146.4. I missed the point in that one point. Okay. Question 2. Graph the order pairs x and y, all these order pairs here, on the coordinate plane provided, right there. What do you notice about the graph? Well, let's graph them. So when I graph it, my points would look like this. Okay, I have in 1 minute almost 40, right? 36.6. In 2 minutes, I have almost 80, 73.2. In 3 minutes, I have slightly over 100, 109.8. And then at 4 minutes, I have 146.4 right there, just above 40. Sorry, I'm not showing you the numbers. There they are. Okay, so I've graphed it. What do I notice? What do you notice about the graph? Well, I notice that the points seem to be in a straight line. And it makes sense that the points are in a straight line because it's a proportional relationship. The rate of change is always 36.6. Right? Well, here it increases by 1 along the sides. It's always going to increase. For every 1 down here, it'll be 36.6 more on our range. Something to take note of is sometimes functions are written using 2 variables. One variable, usually x, represents the domain, and the other, usually y, represents the range. Okay, so x horizontal, y vertical. When a function is written in the form, it is an equation. Okay, when a function is written in this form, it's called an equation. Like equations, functions can be represented in words, in a table, with a graph, and as ordered pairs. The graph of a function is the set of ordered pairs consisting of an input and the corresponding output. Let's take a look at this other example here where the school store sells book covers for $2 each and notebooks for $1. Tony has $5 to spend. The function, the total, which is y, equals 5 minus 2x represents the number of book covers x and notebooks y she can buy. Graph the function. Now notice here, okay, we have to, each one is costing $2, right, each cover, and the x is going to be the number of covers purchased. Okay, we have to subtract that from the $5 she has so that we know how many she can buy. Okay, so the number of books, interpret the points on the graph. Okay, so here we have, she buys 0, she'll still have $5. She buys 1, she's only going to have $3 left. She buys 2, she's going to have $1 left. If she tries to buy 3, she can't, because she'll have -1. You can't have -$1, right? So the maximum she could buy is right here. It's 2, and she'll have a remainder of $1. So 2 books at $2. You subtract that amount from $5, and you have $1 left. And this is what it would be as a graph. It's a negative slope. Okay. And once we've determined that, since we can buy 2 here and we have 1 left over, we already know that a notebook is $1. So my conclusion would be she cannot buy a negative amount. So she can buy 0 covers and 5 notebooks, 1 cover and 3 notebooks, or 2 covers and 1 notebook. That's all the combinations that she can buy. There's all the possibilities. You see that? Okay, so 0x, 0 notebook, 0 covers, 5 notebooks. Each notebook is $1. That's the combination. She could also buy 1 cover for $2 and 3 notebooks, $1 each. Or she could buy 2 covers and 1 notebook. But this is not possible. Okay, let's try this one here. If you think you know how to do it, please pause the video now. I hope you paused the video. The farmer's market sells apples for $2 per pound and oranges for $1 a pound. Marjorie has $10 to spend. The function y equals 10 minus 2x represents the number of apples, because apples are $2, and oranges y Marjorie can purchase. Graph the function and interpret the points on the graph. So these are apples and these are your oranges. So for example, I start off with $10 and I'm going to subtract $2 per bags of apples. Once I figure this out, this over here is going to tell me how much money I have left over, which is to be able to buy oranges. Okay, so let's try it. I can start by saying I will buy 1 bag of apples, 2 bags of apples, 3 bags of apples. Okay, at 1 bag of apple, it'll look as 10 minus 2 times 1. At 2 bags of apples, it's going to look like 10 2 times 2. At 3 bags of apples, it's going to look like $10 minus $2 per bag, and I'm going to get 3 bags of apples. Right, when I do that, I multiply 2 times 1 equals 2, and minus 10, subtracted from 10 is 8. Over here, I have 2 times 2 equals 4, subtracted from 10 is 6. And 2 times 3 is 6, subtracted from 10 is 4. I think I can buy more. I buy 4 bags, and I have 10 minus 2 times 4 equals 2. So with 2, I could even buy 1 more bag, right, of apples. And I have, at 5 bags, I have 10 minus 2 times 5 equals 0. So that means once I get 0 here, it means I cannot buy any oranges. But here, okay, with $2 left, I can buy 2 bags of oranges. Here I can buy 4 bags of oranges. Here I can buy 6 bags of oranges and 8 bags of oranges. Okay, I've picked my x coordinates and y coordinates and put them in here in my order of pairs simply by taking them from here. Okay, and now I'm ready to graph. I can take my graph and put these dots on them, these coordinates. And when I graph it, I get a linear function, a straight line, and it shows here that when I get 1 bag of apples, I can only get, sorry, I should put it around here, apples, right? And over here, oranges, right? So when I get 1 bag of apples, I can get 8 oranges. At 2 bags of apples, I can only get 6 oranges. At 3 pounds of apples, I can get 4 pounds of oranges, and so on. Okay, so you can see. Example 2. Okay. Y equals 2, x plus 2. Make a function table, like we've done in the past. Select any 4 values for the domain, okay, or x. Substitute these values for x to find the value of y, and write the corresponding order pairs. Okay, and we've done that before. We choose any random x, we add it to the rule, we get our output, our y, and then we have our order pairs so that we can graph. Graph each order pair. Draw a line that passes through each point. Okay, once we have that, we know that this can continue, if we continue this pattern, infinitely in either direction. The line is the complete graph of the function. The order pair corresponding to any point on the line is a solution of the equation y equals x plus 2. So yes, any point on this line that we've drawn is equal to y equals x plus 2. That's the equation. So this line is this equation. Okay. So now this is where the fun really begins. Let's start choosing random x values. Okay. And then we solve to get y, and we have our order pairs. First, you must create a table, then list all your order pairs, and then plot them on your coordinate plane. Okay, please pause the video and try B on your own. Pause now. I hope you paused the video. First, create a table where you have your x, your rule, and your y, your output, your input, your rule, and your output. I'm going to choose, okay, maybe -1, 0, 1, 2, and 3, right? And I will put in my rule, x minus 5, or at this point, instead of writing x minus 5, I can simply go right ahead and replace that variable x with my new input. So this would be -6, right? And then I have 0 minus 5 is -5. And 1 minus 5 is -4. 2 minus 5 is -3. And 3 minus 5 is -2. So my order pairs will look like this. And now we're ready to plot, right? I will start with -1, -6, -1 goes this way here from 0, 0, -1, and then -6, 1, 2, 3, 4, 5, 6, right there. So I can put my first dot there. Okay. Let me check that again. 1, 2, 3, 4, 5, 6. Very good. And then my other one's 0 and -5. So I just 0. I don't go left or right. Stay on the y-intercept or y-axis, and I go all the way down to -5 right there. Okay. And it looks like my next one is 1 and -4 right there. And 2, -3 right there, and +3, -2 right there. So I can make a line, and any point on this line, or this equation, equals any point on this line. There you go, y equals x minus 5 is this line. There we go. For C, let's do the same. Let's pick our values. I will stick with my values of -1, 0, 1, and 2. Okay, and I'm going to enter in my rule. 2. Right here's my rule. Right, this is my rule to get y. -2x. So -2 times -1. -2 times 0. -2 times 1, and -2 times 2. And then -2 I get +2. I get 0. -2 times 1 is -2. -2 times 2 equals -4. And there's my input and output. Now my order pairs are -1, 2, 0, 0, 1, -2, and 2, -4. So now we're ready to plot on our field here, on our coordinate plane. And here's what I get. I get -1, 2, 0, 0, right in the middle. 1 and -2, so we go 1, -2, and then finally 2, -4. I go +2, -4, and there I go. I can draw a line here. So the equation y equals -2x looks like this when we graph it on the coordinate field, or the coordinate plane. Next example. Let's get familiar with the vocabulary that we talked about when we first started the video. But first, let's look at the key concept, okay? In words, the value of y is 1 less than the corresponding value of x. Here we have, see, the value of y is 1 less than whatever value we choose for x. There we go, that's how you would say this equation in words. The order pairs, whatever we choose for x, 0, 1, 2, 3, okay, will always be 1 less than y. It's telling us right here, whatever you choose for x, y will always be 1 less. So you see, 0, 1 less than 0 is -1. 1, 1 less than 1 is 0. 2, 1 less than 2 is 1. And finally 3, 1 less than 3 is 2. So here's our order pairs when we take our x and y's, and then when we graph them. Okay, this is the main point of this entire video. So, a linear function is a function in which the graph of the solutions forms a straight line. Therefore, an equation of the form y equals mx plus b is a linear function. A function can be considered continuous or discrete. Continuous data can take any value, so there's no space between data values for the given domain. Discrete data have space between possible data values. Graphs of continuous data are represented by solid line, and graphs of discrete data are represented by dots or a dotted line. Okay, so continuous data, the number of ounces in a glass, the weight of each chocolate chip. Okay, so this is continuous data. If you change the number of ounces, it'll change the value, the amount or the weight in the glass. And the weight of each chocolate, if you take away one chocolate chip, it'll change the weight accordingly. But discrete data, the number of glasses in a cupboard, or the number of chocolate chips in a bag. This is not easy to just tell by looking simply at the data, okay? Or looking at, if you were to stare at a cupboard full of glasses, or if you just look at a bag full of chocolate chips, you wouldn't just be able to tell. You can determine if the data model real-world situations are discrete or continuous by considering whether all numbers are reasonable as part of the domain. Okay. Example 3. Here we go. Each person that enters a store receives a coupon for $5 off his or her entire purchase. Write a function to represent the total value of the coupons giving out. So the total coupons being given out, that would be y. So let y represent the total value of the coupon and x represent the number of people. The function is y equals $5 per person, right? And that would be the total number, the total value, okay, of coupons. So $5 for every person giving out. How many coupons in terms of value did we give away? If we had to choose order pairs, we could do this. 5 people came in, so 5 times 5, we gave away $25 in value, right, for the coupons. If 10 people come in, 5 times 10 is 50 people, or $50 in value. 15 people come in, you multiply the 15 people times the value of each coupon, which is $5, 75, and so on. You can see that this is a linear function. Exactly, here's going up by 5 each time. Over here it's going to go up by 25 each time. Okay, so it's not only linear, it's proportional. Okay, and here we have it graphed. You see, 5 is 25. Okay, 10 is 50, 15 is 75, and 20 is 100. And it would make a straight line down that we go by 0 through 0, 0. Right? Okay, let's try the example. A store sells assorted nuts for $5.95. Okay, this is our constant rate of change, right? This is our fixed value or our slope. $5.95 per pound. Write a function to represent the total cost of any number of pounds of nuts. So our total cost can always be represented by our y. Our change is $5.95, constant change, and the number of nuts can be represented by x, right? So this is the number of pounds that we're going to multiply by the price of the nuts. That'll give us our total number, okay, our total cost. Our total cost. So let's complete the function table below to find the total cost of 1, 2, 3, 4, and 5 pounds of nuts. So we're going to find the total cost, okay? It looks like the numbers have been chosen for us right there. So we're going to go ahead and just make that our input, our x, 1, 2, 3, 4, and 5, right? Our rule has already been given to us, which is right there, right? Our rule, $5.95 per pound, or times x. So we simply replace the variable x with the number that we chose for x. So 591 times 1, for 2 is 595 times 2, for 3 is 595 times 3, and so on. And now we have our output, or our y. So we multiply 595 times 1 is 595, right? 595 times 2 is 1190. 595 times 3 is 1785. 595 times 4 is 2380. And 595 times 5 is 2975. Okay, there's our total costs for the number of pounds with our constant rate of $5.95 per pound. Now we can graph this. I'm going to make my domain is my number of pounds. Okay, that's the number of pounds purchased. And my range is going to be my cost. How much it'll cost for those in dollars. Right? And now we can go ahead and graph. So when I graph it, for 1 pound I have almost 6, right? 5.95. For 2 pounds I have almost 12 right there. Okay, which is 11.90. For 3 we said we have 17.85, almost between 15 and 20 right there. For 4 pounds we said it was 23.80, almost 24, so almost 25 right there. And for 5 pounds it would be close to $30, which is $29.75 right there. And we can make a straight line going through all those dots, so we can say that our equation y equals 5.95 times x is any point on this line. Okay, and that's all the examples for today. Here's your guided practice. Please take a look at your guided practice carefully. Make sure that you feel comfortable with the content. If you do not, go back and look over the examples again in the video, or simply come to class with some questions. Okay, I'll see you in class, everyone.